Hello and welcome back to Marquette University on a nice evening for some irrotational fluid mechanics. So tonight we're going to talk about circulation. It's a short little lecture, but it's an important one just to shore up some of the ideas that we introduced last time. So the objective of this lecture is to develop circulation as an idea theoretically, a little stronger than we had, and then connect that circulation to vorticity via the Stokes theorem. And then I'm going to briefly introduce the Blasius theorem, and then I'm going to re-examine our irrotational and rotational vortex in light of what we learned about circulation. All right, so here's the idea. We've got some streamlines here, and I'm showing psi 1, 2, and 3 streamlines flowing in some arbitrary XYZ space. And I've also shown this closed contour here. And along this contour, we have a velocity that makes some angle ds with the unit normal. So what we would like to do is resolve this velocity along the unit normal, ds. And so that is what we're doing right here. And then we would like to multiply it times ds, essentially this unit normal length, and then sum it up over this line integral. So as we go around the line integral. So that circle that we make along this closed contour is what this little circle means right here on our integral sign. So we're not summing the area under the curve, we're summing along this contour line. What we'll show is that this is the same as just taking the dot product, right? By definition, that's what the dot product is between any two vectors. It aligns one vector to the other. So we're going to align the velocity vector to this arc length ds. And then we're going to show that this line integral can be related to a traditional area under the curve integral by taking the vorticity and dotting it with the unit normal relative to the area. So the vorticity in the area that you see here. So it would be the sum of the vorticity under that curve. All right, so that's essentially Stokes' theorem. And so what I'd like you to do here is, this is by definition what our vorticity is. It's the sum of the velocities in a circle. So you can imagine that if the closed contour is a circle with all the same velocity, it should sum to some quantity. And then likewise, we should be able to perform the integral, the area of that quantity within that area. So this is what I would like to kind of prove right now in terms of the fluid mechanics. So let's start by assuming that the velocity at any point xy is finite and it's known, and it has components u and v. So this is our coordinate system, and then you can see that it has coordinates, scalar coordinates u in the x direction and scalar velocity v in the y direction. So let's pick some closed contour that I'll define here by this dotted line, and then the sides of it will be this 2 delta x and 2 delta y. So it's an easy contour to integrate over because it's normal, right? It's orthonormal. Now, a long time ago, earlier in this lecture series, I introduced the idea of a Taylor series expansion. So what I'm doing here is I'm expanding the velocity in a Taylor series expansion, a first order Taylor series expansion, or one term. So I've got a velocity here that is known, that has uv components. And I just want to know what the velocity is along this surface. Well, that's by definition what the u velocity is, right? And so it's u plus some linear approximation, partial u, partial y, times the distance du, and that would be a first order Taylor series expansion. And likewise, I've done it around the circle. When we come down, we're looking for the Taylor series expansion at y plus dy, so that's u minus partial u, partial y times dy. So these are basically a representation of the velocity expanded to the surface of our contour. All right, so according to what the definition is, we just sum the velocity along this contour and we'll work in a counterclockwise direction. So I'm going to start down here. I'm going to start with that guy right there. So that's the velocity along this closed contour. That's the velocity component, and it's in the I direction. And then I'm going to sum it with, or dot it, I should say, with this arc length here. So that's 2x, and its unit normal direction is I. So together, that would just be 2x times this u minus du, partial u partial y times dy. Now when I move around the circle, there's a little bit of, you got to be careful with the sign here, right? So when I come up along this side, this is the velocity here. But, whoops. This is the velocity here. And the unit normal points in the positive j direction, so I get a positive sign here. But when I move along this way, along the top, I have to stay counterclockwise. I still have the same velocity here, which is positive, but the scalar quantity, the unit direction of that is now pointing in the minus I direction. So I get this minus sign here as a result. In the same way, when I come down this side, I'm moving in the minus j direction. So that's where this minus sign comes from right here. So just be aware that truly is a vector. All right, so if I look at this, a lot of these terms cancel, right? So, for example, this term cancels with this term, and this term cancels with this term, and that term. So we end up with a simpler expression, this guy right here, which simplifies down to just what the definition is of the vorticity in the z direction, dotted with the unit normal area A, where dA is defined here, right? That's the area of the box. All right, so this being the case, we just showed that this is exactly equivalent to this, so we'll generalize this to any 2D coordinate system, that the circulation around a closed line integral of v dot ds is equal to, really it's equal to del cross v, which is the vorticity dotted with the unit normal dA. So don't forget, if you look this up online, a lot of times you'll see this listed as del cross v, right? And that's the original definition of what vorticity is. All right, so again, just to reemphasize, this line integrals the sum along that contour of the quantity v that's aligned to the arc length ds, and that's exactly equivalent to what the area under that curve is of del cross v. It's important for Stokes' theorem to be applicable that the velocity v should be defined properly, meaning it should be continuous and differentiable over the area, continuous, finite, and differentiable over the area, and the area should be connected, right? You can't have any holes in this arc length that you make. And you might remember in Cal 3 you did some of this where you'd go in and you'd make a little circle around singularities and things. All right. Now the Blasius theorem, I'm not going to spend a lot of time on it because it's kind of, it's a little bit, I don't want to do too much in the complex plane here, but essentially realize that we can relate the drag force and the lift force in a single expression using the Blasius theorem. And so really the drag is the real part and the lift is the imaginary part using this complex description, Z. If we insert Bernoulli equation for what the pressure is, we get this expression here. So since this is, the Blasius theorem includes the lift and the drag in one expression, it's more general, but I think it's just added complexity that we don't need at this point. But I did want to just introduce it that we could express the lift and drag as a single function, and this connection is known as the Blasius theorem. All right, so we're down to this example. I'd like to show this example of calculating circulation for our rotational and our irrotational vortex. So you can recall that we several times. The rotational vortex is described with this velocity here, basically the solid body rotation. So it's omega r is the linear velocity component of use of theta. And it's easy enough to calculate the vorticity of this. It's just del cross v, and so it ends up just to be 2 times the rotation. By definition, 2 times the rotation of the solid body. Vortex, which is also known as a free vortex, it is k, which is some constant magnitude of the vortex, or the strength of the vortex, divided by r. Decay over r as you go to infinity. And the velocity of this vortex is equal to 0. It's called Untitled Vortex, right? All right. So let's use our newfound definition of circulation to calculate what the circulation of each one of these vortices is. So this is our definition of circulation here. And let's integrate along a streamline. So let's pick a contour that is a circle where r is equal to some constant r, and we'll insert it into this equation here. And since I know what omega is, insert right in, and for r d theta, and over the line integral. So that's 2 pi r, right? Right, over pi r squared, which is this area. I'm sorry, line integral. We're doing this sum. So it's this area, which is pi r times k. So k is the unit mole out of the plane. Okay, so anyway, you can see that if I dot k with k, those annihilate each other, and I end up with this 2 omega times the area. So that makes a lot of sense, right? All right, now let's do the irrotational vortex. So this one we have the velocity and the vorticity, and if I define if my definition of what vorticity is or the circulation is, both as a line integral and as a contour or an area plot integral, then we can calculate the circulation using the vorticity. So if the vorticity is 0, it seems obvious that if I just put 0 vorticity in there and I try to take this integral, I'm just going to get that the circulation is 0. If we use the line integral definition of velocity, so if I use the velocity, if I insert the velocity here, k over r, into my definition, and now my unit length, arc length, is 2 pi r, which is the arc length around the circle. This actually integrates to a quantity, right? The r's cancel, and I end up with 2 pi. So how can it be? How can I have 2 different solutions for the circulation? Well, the answer is that there's a singularity at the origin, right? Velocity at the origin. If the velocity goes to infinity at the origin, it means that this version of the definition is a little suspect. So what we do is there a discrepancy between the two? And not really, because the velocity is not continuous over the entire area. We violated the assumption that was key to the Stokes theorem, and that is that the velocity be continuous over the area. So what we do is, if we pick a contour, such as a blue contour here, that includes the origin, right, then we have to follow our kind of baseline definition. We have to include, or we have to use the basic definition of what the circulation is. And in that case, we get that the circulation is pi k. If we include a contour like this dotted blue line that I'm showing here that doesn't include the origin, so that it doesn't include the circulation, then we can use the definition of circulation as the area of vorticity. And so in that case, the circulation for the irrotational vortex is 0. And it's interesting to recall at this point, when I compare this solution, you can see that gamma, the circulation, is equal to 2 pi k. And if you recall, when I first introduced the irrotational vortex, I said that Some authors like to report the irrotational vortex as K over R, like this right here, and some authors like to report the definition of what the velocity is for the irrotational vortex as gamma by 2 over R. So they're the same, and you can see why, you can see where these definitions come from. All right, so to wrap up here, we became more familiar with circulation and its concepts and what it means. We ran through these are actually 5 here, 1, 2, 2, 3, 4, but we ran through these 5 different exercises. And next time we're going to examine the flow associated with an infinite row of line vortexes, which forms a vortex sheet. And so we call that the vortex sheet. All right, so that's it for tonight, and we'll see you hopefully again next time. Take care.